Hey everybody. I hope you guys are doing better than I am. Um, so let's get right into it. You should already have the student template downloaded from Excel, Canvas. You should have entered your data. Um, let's just go over the sheets. The very first sheet is just an example sheet that really does show you the breadth of what we're going to be doing. But you can click on the strong acid, strong base sheet and yours will be empty. So right here, you'll enter all of the milliliters of base that you collected along with the pH values that you collected. And I just have those in yellow so that they stand out. Maybe yours are in yellow already too. I've also highlighted some background colors for my pH calculated column. Each of these different colors represents a different equation type that we're going to have to use. And then if you click on the strong acid, strong base curve, once you've entered your data, you'll see that it generates a line. So this line represents the data that we gathered in class. We're going to, on top of this graph, put another calculated line that gets filled in automatically when we fill in the calculated pH at all these different points in the titration. Initially, I believe this might be empty on yours. I don't remember when I filled it in. But we started with the HCl concentration being 0.1. We started with 25 milliliters of HCl in the flask. And you guys recorded how many milliliters it took to reach the endpoint. This was gathered during the initial titration with the color changing. So those were the two pieces of information that you sort of recorded. Um, so one of the first things we have to do is calculate the concentration of base. So the base concentration really is just equal to the amount to the moles of acid added over the new volume, right? So what we got to do is we got to figure out how many moles there was inside that acid we added, and we need to divide that by the amount of base we added. So the volume of base on bottom, the moles of base on top, right? The moles of base is equal to the acid moles added. So we can calculate that right here. We can say, well, first, so we'll say equals, and I'm going to put a parentheses. We need to know the number of moles of acid that was there. That you get by multiplying concentration by volume. So we've got those numbers right here. So I'm just going to grab the concentration of acid, Shift 8 to give a multiplication. We're going to click on the volume of acid and close parenthesis. So if I was just to hit enter right now, we would be left with the moles of acid. Those moles of acid presumably are equal to the moles of base, right? If that was the mole, if we got to the neutral point. So right there, I could, right there, I have the moles of base. So if I divide that by the actual volume of base, the 21.5 in my case, or the amount that it took for you guys, then what we have here in this calculation is the concentration of base. So I'm going to hit enter. And so you can see for mine that it means my base is a little more concentrated than my acid. And that makes sense. That's why it took less base to neutralize that acid, right? If they were both exactly zero point 0.1, then it would have taken equal volumes. Okay, so we have that base concentration. The next thing we need to do is we need to fill in all these columns. So these are easy. So let's just get into it. So this millimoles of acid. Millimoles of acid is just going to be the concentration of acid times the volume of acid. So that's just the amount of acid present. And that's not going to change. That's actually going to be the same number, this entire column. To find that, we just need to multiply the acid times I'm sorry, the concentration of the acid times the volume of the acid. So I'll do that. And it's 2.5. Now, if I wanted to be able to drag this column down, I actually need to go in here and add dollar signs. I might as well do that. You could also save yourself this step and just write 2.5 in the next cell and then drag that down. Because 2.5 is the number. It's not going to change. But by adding those dollar signs, now it applies that exact same calculation the entire way down, and it'll be 2.5. So that's the amount of acid that's in there to start with. All right, millimoles of NaOH. This is how much base we're adding at any given moment. This is just the concentration of base times the volume of base, but the volume of base changes, right? It's over here. So to set up this equation, we're going to say equals, we're going to absolute reference this concentration. We don't want this to change. We want this to stay G5, the whole column. So I'm going to put dollar signs in front of it. And we're going to multiply that by the amount of base added. So that's just this column A. And if we hit enter, it should say 0 for 0 moles added, right? The initial pH reading. If you don't have an initial pH reading, if the first pH reading you took was after you added something, then just on the 0 column, like insert another data point and just put a 0. And, I suppose you won't know the pH, but you'll see that we can at least calculate the pH, even if you don't have a pH observed. Okay, so it's 0. But as I grab this and drag it down, you'll see that that number gets bigger and bigger and bigger. So I'm going to just drag this. We can drag it all the way down. But at some point, you're going to see that it becomes bigger than the amount that we have, the amount of acid we have. So, and that should happen at the neutral point. I have an exact neutral point here. This is mock data. You probably don't have this exact point where your pH was 7. That's okay. You will see a point, though, where the amount in this column starts getting bigger than the amount in this column. I usually like to just change the color of the background when that happens. You don't have to do it, but I like to just give myself a little bit of a way to know I'm dealing in a slightly different sort of calculation space. Okay, so that's where we exceed the amount of base or acid present. Moles of excess. This is how many more moles of acid there are than base. It's basically the difference between column D and column E. So we can say equals. I'm going to click on column D, and then I'm going to say minus column E, and hit enter. And so here the moles of excess hasn't changed. It's still 2.5. But as we drag this down, you'll see that that number gets smaller. So there's less and less excess. At one point, they're actually going to reach the exact same number. And then if you continue, then those go negative. I'm gonna get rid of that filling. Okay. But I am going to note again over here where this thing goes negative. Or maybe we'll save that for later. We'll save that for later. These negative numbers we can repurpose towards the end. All right. So we've got our moles of excess. Total volume. Total volume is just the amount of liquid in the flask. Initially, it's 25. It's this number here, right? 25 mils plus whatever's in column A. So we could just put equals 25 plus, and then, hit column A. But if we want to be fancy, let's reference this cell, but let's put dollar signs in front of it. Dollar sign G, dollar sign 3. So it's this volume, 25, plus the volumes in column A. So this one shouldn't change. It's just say 25. But as we click it and drag down, it should give us the final volume of everything. So 25 plus 27, right, is 52. So now we have a way of including volume in our concentration measurement. The last thing to do is just to determine the concentration of hydronium, right? From that, we can get the pH. That's just going to be however many moles. Let's see, don't know why I have this here. Sorry. I guess it'll go away. Or maybe it won't. We're going to take everything in column F, right? The amount of excess acid there is, and divide that by the volume. And that'll give us a current concentration of hydronium. That's just equals whatever's in column F divided by, divided by whatever's in column G. And so that gives me a concentration. Now I'm going to drag that all the way down to the neutral point because it doesn't really make sense to have negative concentrations. Um, so we'll save this area for calculating something else. Let me give it a slightly different color hue. We'll save that for something else. I mean, once we're into the basic territory, right, we're not really calculating hydronium anymore. We're calculating hydroxide. And so I just want to make sure that I'm prepared for that change when it happens. Okay, that's good. It's a nice bright color. I'm even going to label it. I'm going to put OH down here, just so I know. But we're not there yet. All right, columns are all filled in. Now to calculate pH at this point right here, we only need to know the concentration of the acid present. So just the negative log of whatever this guy right here is, right? In fact, sorry, I don't think I need a red one actually, because I think this isn't a buffer system. So yeah, my bad. I don't actually need this to. It doesn't matter. Will that change it? Yeah, it doesn't matter. It doesn't matter. Let's see. Copy, paste. Sorry, I'm just thinking about something that doesn't matter. Oh no, what's going on here? My Excel's wigging out on me. Sorry, give me a second. I don't know what I pressed. Now I can't seem to go back to full screen. All right, sorry. Let's just yeah, I let's just calculate it so you can see. All right, negative log. It equals the negative log of the concentration of hydronium ion. We hit enter, and we get a pH. Um, we should be able to just drag that all the way down and watch as the pH increases. Yeah, for the weak acid and weak base titrations, the initial pH calculation at the top is different than the meat of the rest of them. But for a strong acid, strong base titration, this calculation is actually just one big calculation. When we get here, we got to remember that when there's equal amounts of acid and base, then the pH is just equal to the concentration, or what is it, 10 to the minus 7, right? Because the Kw, I suppose we need to know the temperature of the water, but the Kw is 10 to the minus 14, and that means that each hydronium and hydroxide represent 10 to the minus 7. So here for calculation, we could put that it's equal to the negative log of, let's see, 10 to the negative 10 raised to the negative 7. All right. Now here, we are no longer dealing in hydronium, we're dealing in hydroxide. And so since there's just base present, we need to figure out first the pOH. We can take the negative log of the hydroxide concentration, but then we'll use the relationship between pH and pOH to figure out what the pH is. So hydroxide. Now, how do we find out how much hydroxide is present? Well, the hydroxide that's present is equal to the excess hydroxide that we added, divided by the, or well, I want to say the moles of the excess hydroxide divided by the volume. We actually have these numbers, all these negatives right here. This is how much more moles of base there are than acid, right? This is the excess of that hydroxide. What we want it to be, though, is not a negative number, so we can use it. I mean, I suppose it really doesn't matter. Yeah, we don't need to change them to be positive numbers. That might be confusing. But let me show you how we can get the concentration of hydroxide now. Assuming this to be the concentration or the moles of hydroxide, and this is the volume of hydroxide, we should be able just to take one over the other. So I'm actually going to insert a -1 in here, though, just to get rid of the negative sign. But to show you that the calculation works, we're going to say it's just the moles divided by the volume, right? And so we get this concentration, but it's negative. Two ways to fix it. One way is just to switch the order in which we subtract column D and column E, right? To get this. Here we were doing D minus E. We could easily just go E minus D. And now it's a positive number. And now, all of these are positive numbers. And now these are all positive concentrations. We could do that. Or you can just multiply it by -1. I think I said I was going to do one and I did the other. But either way, that's why I had highlighted this area, just so I could visually see where it is that I want to maybe flip the sign or, subtract differently. But I hope you understand that that's what we were dealing with these numbers here. These were the excess moles of base. So since we have that number, we can divide that by the volumes and we can get the concentrations. So over here, we could put into our equation negative log of, column H, but that's going to give us POH. So I'm going to put a slight addition to our calculation here. I'm going to put 14 minus in front. That way it takes our POH that we're about to calculate and flips it into a pH. So 14 minus, I'm going to put a parenthesis in here, the negative log, and I'm just going to click on this number, column H, and then close parentheses, close parentheses. Sorry about that blue color not being a good choice there. Change that to a yellow. So now you'll see that equation up here at the top, you can see it, 14 minus the negative log of column H flips that POH into a pH. Now we drag this whole thing down. So it's all filled in now. And what we do is we look at the curve, and mine deviates a little bit. The shape's right. Doesn't exactly match up with the numbers that I saw in class. Our pH meters are disagreeing a little bit with what the theory is, or at least what those numbers would actually predict. Our concentrations could be wrong or could be slightly off. But there we are. So that's strong acid, strong base. That's by far the easiest one. The next ones are a little tougher, okay? So we'll switch over to doing this one now. All right, a few things that we need. One is we need that concentration of base from the other page. So I'm gonna go grab it. What you could do is also you could hit equals and then just go back to that other page and click on it. And that way, even if you were to go in here and change this number, it would automatically, I'm gonna hit enter. It would automatically update onto this page. So rather than just copying and pasting it, you can just have it reference that other cell. Okay, so what else are we gonna need in here? Looks like we have our starting concentration of acid. Do we know that? I don't think we know that. We have to calculate that. We have the amount of acid, 25 mils. We have the endpoint that you would have figured out in the first part with the indicator. And then we have our concentration of base that we know. This is acetic acid, so we also know the Ka. It should be given. If it's not given on your Excel sheet, it's 1.8 e to the minus 5. We're going to need a pKa. A pKa is just equal to, what is it? The negative log of the Ka. So let's go negative log. So 4.74. We're going to need a pKb for when we get past the neutral point and we are dealing with the I'm sorry, when we get to the neutral point and there's only conjugate base present, we're going to need the pKb. So that's just 14 minus the pKa. And then we are also going to need the Kb. Well, I suppose we just need the Kb, not the pKb, but that's why I have the pKb here is because it's a lot easier to get, I think, the pKb from the or the Kb from the pKb. It's just 10 raised to the negative pKb, right? 10 raised to the negative pKb is your Kb. So we have that. Let's see, can I make that scientific notation? It's a little nicer looking. All right. I think those are all the number. Oh, we need the concentration of acetic acid. So that's just the moles of acetic acid present divided by the volume of acetic acid present, right? Which is 25. We said the endpoint happened when this concentration of base and this volume of base were used. So we can multiply those together to get moles. Those moles should be the moles of acetic acid that were present, and then we'll divide by this volume. So let's do that. So this is equal to parentheses the concentration of base times the amount of base, close parentheses. So that's the moles. Technically, that's the millimoles. They should be equal at the neutral point, and we're going to divide by 25, or divide by this number, mils of acetic acid. H5 times H4 divided by H3. I suppose you could have done H4 times H5 also in that order. All right, so we get this concentration of our starting acetic acid. We got to fill in these columns. So a lot more of what we did last time. So millimoles of acid, that's just the amount of acid. So we'll say equals the concentration of acid. I'm going to add absolute reference times the volume of acid, also absolute referenced. Enter. And this number is the same number all the way down. Millimoles of base added. This is just the equal to the concentration of base, absolute referenced, times the volume added, column A. So it's the amount of base, column A. I'm going fast, I'm sorry, because this is a long titration lab, and I assume you guys will pause this. So if you're not pausing it, realize that you can pause it after each one of my steps and then like catch up. We hit enter. And if we drag this all the way down, at some point it will exceed that number. I don't know that there's an exact point here where it happens. Of course, this is fake data. So I think it happened right there. And I'm just gonna, again, make this yellow. So I know when those numbers will be the ones next to the negative ones that we get here at some point. So millimoles of excess HA. This is just column D minus column E. And we can drag that all the way down. Here where they go negative is where we'll be dealing with the base only situation. This will all be excess OH. We can probably premature to make a column there. Oh yeah, way premature. Total volume is going to be equal to the original volume, which is 25, absolute referenced, plus the amount added, so column A. And we, again, can drag that all the way down. So now we have our way of calculating molarity from the final volume. All right, and here we go. So HA. So these columns are really important for our Henderson-Hasselbalch equation. The orange section that I have here under pH calculated. This is all buffer zone. So we're going to need those numbers. But initially, there's only acid present. But it's not a strong acid, so we can't just say negative log. So what we need to do is we need to figure out we need to use the Ka equation. The Ka is equal to x squared over HA minus x, right? That equation. We need to do that. So what we want to do though is we need to solve for hydrogen ion. We need to solve for x in that equation. Which means we need to know what the Ka is, hence why we have it here in a clickable cell. And we also need to know what the starting concentration of HA is. So let's get that starting concentration of HA. In fact, we'll just do the first column, but I feel like we would just drag this all the way down. The concentration of HA is equal to the amount of moles of HA, so column F, divided by column G. Yeah, I'm pretty sure we just drag this all the way down. It may not make sense down here in the negative zones. Yeah, anywhere here past 0, it really doesn't make sense. So I'm just going to cut it off right there. Okay, so now we have that. So let's see what this equation for pH calculated is going to look like. I'm going to get rid of the color here just so that it's easier to see. All right, equals. Now, I'm going to build this from the ground up, so we're going to have to go back and insert negative log unless you are okay with me putting that in at the beginning, but kind of want you to understand what we're doing. So we want to get x. We want to know what x is in that equation of Ka equals x squared over HA minus x. So we need to get x by itself. Well, we can move HA over to the other side of that equation by multiplying it by Ka. So let's start there. So equals, I'm going to put a parentheses. I'm going to put my Ka in. I'm going to have that multiplied by my HA. Okay. But all that, right, only gets me x squared. That doesn't get me x. So I actually want the square root of this number. So maybe back in here in my equation, I'm going to add the square root. So right in between the equal sign and the parentheses, we're going to put square root. So now you'll see my equation is taking the square root of H6, which is the Ka, and H9, which is the HA. But that's just giving me x. That's not giving me the pH. So in front of all of that, we actually need the negative log. So let's go. We're going to add right after the equal sign, negative log. And now I'm going to go and pop in another parenthesis at the end. Just want to make sure that I've got enough parentheses front and back. So now it's the negative log of the square root of the Ka times the concentration. I'm sorry, Ka times the concentration. So that's the first type of calculation, right? That's pH before you add anything, pH of a weak acid. So we hit enter. So we got our first point. All right. On this entire orange section, though, we're going to need to use the Henderson-Hasselbalch equation because As soon as we add 1 milliliter of some base, we're going to generate some A minus, right? So let's get that column. So our conjugate base, our acetate, that is just going to be equal to. Now, I suppose we can start at the top. You'll see if we start at the top, it's just going to be a 0 there. But we can do it. So acetate is equal to the amount of base that's added. So millimoles of base in the first part, it's 0, divided by the volume. So we hit enter. And as I drag this down, you'll see that the amount of acetate goes up. And it should go up and up and up all the way until it equals the exact number at this point. Actually, I don't see it equaling anything anywhere. Let me make sure I'm doing this one right. Let's see. A minus is just equal to, yeah, the amount of base. Okay. We're good. I think we're good. Let's just see what happens. Okay. So if you remember a Henderson-Hasselbalch equation, the pH, so back over here, the pH is equal to the pKa plus the log of the conjugate, in this case, conjugate base over the acid. So we're going to say equals to pKa. We have that to click on, but we need to absolute reference that. We don't want it to change to a different number each time. So that plus, now I'm going to put parentheses. Actually, I'm going to put a log. Plus the log. I'm going to put parentheses around that whole thing, though, because I'm extra paranoid. The log of A minus, sorry, we're in on row 10. A minus divided by HA. And I'm going to put 2 closing parentheses and hit enter. Now, the fact that it gave me a pH, approximately near the one that I quote unquote observed is a good sign. Now, I'm going to drag it down, see if it maintains a good signness. Looks like it. So this should make sense all the way up to the neutral point. Okay. All right. Now, we'll deal with this in a minute. Okay, so what about this point right here? This is the neutral spot. For mine, it's an exact neutral point. So there's only conjugate base present. And since there's only conjugate base present, the only thing I can do is use the Kb to find out what the hydroxide concentration is, right? Because since the conjugate base is present and it's a little basic, it raises my pH because there's a little bit of hydroxide being generated. So I can mirror the equation we used up here, right? The log of the square root of, this time it'll be the concentration of conjugate acid or conjugate base times the Kb. But all of this will just be giving me the POH. So I'll need a negative 14 or a 14 minus in front of this whole business. But that's what we got to do down here. But that's why we have the Kb and the pKb ready for us. Well, I suppose not the pKb, but the Kb. All right, so let's try to build this one from the bottom up. First, let me make sure I have everything I need. I'm going to need the Kb, which is up at the top and it's clickable, but I'm going to need the concentration of weak base. So I want to check what this number is right here. This number says that it's E minus G. E was my millimoles of base added. Okay. But I feel like it should be the excess. No, it's just the total amount of moles. So it should be this number divided by the volume. The millimoles divided by the milliliters. Is that what it is? It says it's E divided by G. Yeah, okay. So this is that concentration that I needed. Okay, we can do this. So let's click on the pH. We'll say equals 14 minus parenthesis. So that's going to get us out of the POH back into the pH. Square root, no. Negative log, negative log of the square root of, so I'm doing SQR and then I'm just selecting square root of that number, concentration of conjugate base, times KB for that conjugate base. Close parenthesis, close parenthesis, close parenthesis, enter. The pH looks right. I mean, it's definitely doing what what's supposed to be doing. I'm happy about that. All right. Now we have just excess base. We've neutralized all of the acid, and now we're just adding um, sodium hydroxide. So we can calculate the pH based on just the amount of sodium hydroxide that's there, the POH. I need to make sure I have a concentration of sodium hydroxide here somewhere that I can look at, because I don't think that's what this is. No, we need to look at the excess now. So I'm gonna delete all these numbers right here. We don't need them. They don't mean anything. But I'm gonna repurpose this and have this be where I have my OH concentration. Just make that yellow. All right. What I need for my OH concentration is I just need to know the excess amount of base. So these are the excess moles of base compared to acid, and the volume. So it's column F divided by column G. But I don't want negatives. This time we'll do the negative switch. So we'll go equals -1 times, and then in parentheses, I'm going to say column F divided by column G. And that should have switched the concentration to be positive. It'll make all these concentrations positive, just to check that they're all F divided by G, F divided by G. One more time. F is the excess moles. So this is how many more unneutralized moles of OH there is. So that's the amount of OH that's physically floating around. And this is the volume. So moles over volume is concentration. If we do negative log of this, we get POH. If we do 14 minus the negative log of this, we get pH. So let's go equals 14 minus parentheses negative log of this number. Close parentheses, enter. And I'm just going to drag that all the way down. And it should fill in for you, like it did for me, those high-end pHs on our curve. So if you look at our curve, oh, this one works really nicely. Fits really well. Started off a little wonky. Maybe I did something wrong up here with this calculation, this initial one. I think I did it right. That's how you calculate the pH of just a weak acid on its own. Okay. All right. So what we're gonna do in this one just basically mirrors that, but instead of starting with the KAs and PKAs, now we're gonna start with the KBs and PKBs. We're gonna use a different Henderson-Hasselbalch equation for this green section, because it solves for POH. We're gonna say the POH is equal to the PKB plus the log of the conjugate acid over the base. So yeah, let's just you can take a break and then let's get right back into it. All right. Let's see. Is there anything you don't know here? I suppose we don't really know the initial concentration. Oh, we do. Sorry. I'm thinking of the wrong thing. We don't know the base concentration. We know the acid concentration. We assumed that to be 0.1 from the get-go. Mils to the endpoint, that's the same. You would have figured that out in the first part of the titration with the color change. Mils of base that we're starting with, in this case ammonia, we started with 25. And PKB is KB is given. PKB is just equal to the negative log of the KB. pKa is just equal to 14 minus the PKB. And the Ka is just equal to 10 raised to the negative pKa. All right, we need a starting concentration for our base. This is based on the neutral point and the amount of acid we added. So if we added 23 mils of 0.1 HCl, then those millimoles should be equal to the millimoles of NH3. So we'll say equals, parentheses, acid concentration times acid used. So millimoles of base, essentially, divided by 25, because that's how many mils we started with. So millimoles of base divided by millimoles of volume of base. So roughly on mine, 0.0924. Yours will be kind of different based on what your HCl endpoint was. Millimoles of HCl added. So this is actually going to be the one that increases. So we'll say equals. We'll click on 0.1, but we got to absolute reference this. We'll say times, and then however, whatever's in column A. And this will go all the way down. Millimoles of NH3. This is going to be a static number. Just to kind of show you how we could do that a faster way. We can go equals. We could say concentration of base times volume of base. So it's 2.31. I don't know if that's got more digits or not. Let's see, copy, paste. No, that's not what I want to do. I was going to say we can just go like 2.31 and just drag that down, But just in case that I don't have all the decimals showing, I'm going to go back in here to my first equation and just absolute reference these. And that way, I just make sure that every one of these cells has the exact same number in it. I would hate to have rounded it when it didn't call for rounding. Okay. Millimoles of excess NH3. This is just going to be how much NH3 is still in there as we try to neutralize it. So we should do column E minus column D just to have it be positive numbers. E minus D. And then at some point it'll flip to negative numbers. And by now you realize that that just means that we're dealing in a different sort of part of that. I'll mark it over here. We're dealing with a different situation. All right, and then total volume. This is just equal to, we could just say 25 plus column A. Here we did take a shortcut. Instead of using this number and absolute referencing it, I just wrote 25. But we know it's 25. Right, so then total volume, right, all the way down. All right, we can do these. We don't really need them, but let's do them. NH3. Now, NH3 is present at this point, so we can do this one. We'll just say equals. It's literally the excess moles of NH3 divided by the total volume. And we can drag this down. At some point, it will make sense. Probably right there, it stops making sense. And NH4, we can also drag down to that same point. And it should also not make sense beyond that point. NH4 is equal to the amount of acid added divided by the volume. Remember, the conjugate acid, NH4, is formed from each molecule of NH3 that gets neutralized. And so the amount of NH4 present is related to the amount of moles of HCl added. We should be able to drag this all the way to at least that point. And then maybe beyond that point, I'm going to call this area, again, some other zone. And maybe we call it H plus. Because when we get here, we're going to be dealing in the acidic part of the curve where there's only hydronium present. All right, calculations. The pH. Since what we can solve for here in this basic solution is the pOH, we're going to have to start with a 14 minus. So equals 14 minus. That way, whatever we calculate, it's going to switch from pOH back to pH. We're going to need the negative log. Once we get that pOH, right, comes from the negative log. So log, the wrong one. There we go. It's the negative log of hydroxide, which is the x in our Kb equals x squared over b, or b equation. So we need to now find what x is. Remember, that comes from the square root. So I'm going to do a square root function. And it's the square root of the concentration of NH3 times the Kb. Parenthesis, parenthesis, parenthesis. So square root of concentration times Kb gives us hydroxide. Negative log of hydroxide gives us pOH. And 14 minus gives us pH. We got 11.1 calculated for that. Now, this next step is a Henderson-Hasselbalch equation, where the pOH is equal to the pKa plus the log of the conjugate acid over the base. But again, that's pOH. So we need to start with a 14 minus. So 14 minus equals 14 minus. And now what we want is to go pKb plus, now I'm going to put parentheses just because I'm paranoid, plus the log, log, of the concentration of NH4 divided by the concentration of NH3. Remember, we're in that second column, second row down now, so don't get confused about, don't click on the wrong cell. Row 10 it should be. Close parentheses, close parentheses, close parentheses. All right, I think that worked. Let's drag that all the way down and see how far it'll go. Oop, win invalid. So I must have done something wrong. Is it the pKb minus the log? Is that what it is? Give me a sec. No, I'm right. It's the pKb plus the log of the conjugate acid over the base. What am I doing wrong? All of this should solve for, oh, we we don't want the pOH. What am I doing? Let's see. Let's get rid of the 14 minus for a second and see what happens. Okay, so that's definitely solving for not what we want. This is giving us the pOH. So I need 14 minus that. So what happened? Why didn't it work? 14 minus. So why doesn't it work here? What do I have wrong? H11, I11, 14 minus E8. Oh, I know what happened. I didn't absolute reference properly. I didn't absolute reference my pKb. I need to absolute reference that. $E, $7. There we go. Sorry. So we can drag this all the way down to the neutral point, where we have a new calculation. At the neutral point, there's only conjugate acid present. And I think that concentration is right here. This is the total amount of acid added over the volume added. So this is what we need here is the Ka and this value to solve for hydronium. And then, so it's basically like the calculation we did back in the weak acid strong base right at the beginning. It's that calculation. It's literally the negative log of the square root of those things. So let's do it. Equals negative log of the square root of this concentration of H4 NH4 plus times the Ka. So that's why we bothered to go and have it in a cell that we could click on. Parentheses, parentheses, boom. And now, in order to calculate the situation where there's only excess acid, we just need to know where the excess acid is, and that's this guy. Sorry, this column right here. These are all excess acid. We've got volume right here. So we just need to do column F divided by column G. And I can do that anywhere. I'll do it right here. Equals -1 times column F divided by column G. And close parentheses. And you should be able to drag that all the way down. So these are now positive concentrations of H plus. And to get the pH, we only need to know the negative log of that. So we should be able to just press negative log of this concentration and then just drag that all the way down. And if you've done this right, your graph should again follow roughly closely to that experimentally derived graph. All right. I hope I didn't go too fast for comprehension purposes. But it is a long one, so we do have to move a little quickly on it. I hope I wasn't too confusing with the steps down here with the that's why I like to color code, just so that it keeps my mind from having to think extra hard. We really were only doing 4 calculation types and then just dragging everything down, but it helps to know where those spots are. Um, and just to point out where those are, the first one's at 0 mils added, so that's why that color's there. The second one happens at the point where right before my numbers switch negative. And that's where I know the end of my buffer period is. So then everywhere in between those 2 points is the Henderson-Hasselbalch zone. And then anything after that point, right, where the number goes negative, then you're in the top half of the curve. So hopefully you're able to figure that stuff out on your data. But let me know if you have any questions, okay? Feel free to email.